2.1 Rates of Change and Limits, Part A. This is notes, page 1. Objective. The student will be able to use the properties of limits and use multiple techniques to find the limits of functions. What is a limit? The idea of a limit refers to the behavior of a function near a point, what it's doing, rather than what it actually is at that point. It'll make better sense, hopefully, once we do problems. Here we have f of x equals x squared plus 3. So here we have a graph. It is a parabola. It is x squared plus 3. Suppose we wanted to find the limit of f as x approaches 1. That means where x equals 1, what is the graph doing? This is how we say it. We write it like this. The limit as x approaches 1 of f of x. So this is the proper notation for limits. In calculus, there are several ways to do this. One is graphically. That's with graphs and pictures of graphs of functions. 2 is numerically. That involves creating tables. And 3 is algebraically, and that's just using math and equations to find the limit. Okay, so number 1, graphically. Basically, just use the graph to determine the y value at the given x value. So this is proper notation here. This is how you should write your answers or anything involving a limit. Now look at the graph. Okay, so I'm focused on x equals 1. So I go to x equals 1. Well, here's 1. And that's what I'm going to focus on. So looking at the graph, I see that at x equals 1, the graph is here. It's kind of like the height of the graph. Limits are always the y value. So I want to know basically like how high up is the graph there at x equals 1. So here, this is 1 equals 4. So that means that the limit as x approaches 1 of f of x is 4. And that's how we do it with a graph. I'm just looking at a picture. I'm using the picture to answer the question. Number 2, numerically construct the table of values. I'm still looking for the limit as x approaches 1 of f of x. Still have the same graph. Remember, I do have an equation. I didn't use it last time because we were using the graph, but this time we have to do this numerically. And in order to do it numerically, I have to construct a table of values normally. Usually you don't have the equation and the picture, and then you have to create a table. Sometimes you just have the equation and you create a table. So create a table. Okay, no big deal, sure. Let's see. Let's see, 1, 2, 3, 4. Let's make it 5. So I'm going to need x values, and I'm going to use those to find the y values. So x values, let's see. I'm trying to look for the limit as x approaches 1. So let me place 1 right here. This is what I'm looking for. I'm going to choose or select numbers or x values that are on either side of 1. So numbers that are smaller than 1 and numbers that are bigger than 1. But what I want to do, and what you're normally going to have to do, is pick numbers that are really, really close to 1. So 0.99. That's really, really close to 1. It's not quite 1, but it is smaller than 1. So then you want to pick another number that's really, really close to 1, but it's still smaller than 1, and obviously smaller than 0.99. You don't have to get very creative. 0.9 is smaller than 99 and smaller than 1, and it's really close. Okay, so now I want to pick numbers that are bigger than 1, but with the same idea. I want them to be really close to 1. So I hope the most obvious is 1.01. That's really close to 1, but it's not quite 1, right? It's definitely bigger by 0.01. Now I want to pick another number that is bigger than 1 and bigger than 1.01. So I'm going to pick 1.1. So I've chosen my numbers. Now the idea is that normally I wouldn't have the graph to look at for my answer whenever I have to make some kind of table. So what I'm going to do is I'm going to take the values that I came up with, the ones in blue, and I'm going to plug them into the equation. And hopefully I don't need to show you that, right? So you just take 0.9, plug it in, and when I did, this is what I got. I got 3.81. I'm going to plug in 0.99, and when I did, this is what I got. 3.980. I'm going to plug in 1.01, and I'm going to get the number 4.020. And then I'm going to plug in 1.1, and I'm going to get the number 4.21. Okay, so you're probably wondering, well, why don't you just plug in 1? This is an example of how we're going to use tables to find limits. So this problem is actually a little too easy. Yeah, you could just plug in 1. And when I plug in 1, let's see, f of 1, so that's 1 squared plus 3. I plugged in 1 for wherever there was an x, so that's 1 plus 3, so that's 4. Well, duh, the limit is 4. Congratulations. But when the problem is a lot harder than just x squared plus 3, when it's actually very difficult or impossible to plug in the number whose limit you're looking for, this is an alternative. Creating a table with numbers that are really close, or x values, that are really close to the number whose limit you're looking for. Hopefully you can see from the left, and this would be the left, number smaller than 1. From the left, as I get closer to 1, these numbers, they appear to be getting bigger and closer to the number 4. From the right, and this is the right because they're numbers bigger than 1, and they're on the right. When I'm coming from this direction, as I get closer to 1, my y values are actually getting smaller a little, and they're also getting closer to the number 4. So this is how you do limits from both sides. This is called a two-sided limit, and that is how we use tables. Numerically, we take the two-sided limit, or we find the two-sided limit to figure out, okay, what would be the limit as x approaches 1 from the left and from the right, and both of these numbers appear to be getting closer to the number 4. And that's how you would find the limit. I repeat, this problem is too easy. You could have just plugged it in, but that won't always be the case. Okay. Number 3, algebraically, or also analytically. This is just using algebra, stuff you already know. That is when you're actually able to, because you can't always use algebra. All you have to do is plug in the x. There are other techniques that involve more math, but that'll be the next section. So plug in the x value. Okay, so the limit as x approaches 1 of f of x equals, all right, I kind of already did this, didn't I? Up here somewhere, I took the equation f of x equals x squared plus 3, and what I did was I plugged in 1, and I got 4. Okay, this right here is how you would do it algebraically. You can't always but when you can, it's probably the easiest. Okay? All right. All right, so we're going to do an example graphically, or two examples rather. We're going to talk about one-sided and two-sided limits. Example 1 is evaluating a limit graphically. I have two graphs, so two little examples. I'm going to use the graph to find the limit if it exists. If the limit does not exist, explain why. Now, limits have to exist. And in order for them to exist, the two-sided limits, the two-sided limits must be equal or equivalent or the same. If they're not, then the limit does not exist. Example A. Let's see here. By reading the graph, we should be able to determine the limit of f of x as x approaches 2. So here's 2. Now, here's the confusing part with these kinds of graphs and pictures. If you look, you will see a little black dot right here. Limits have to do with the graph itself, not just random points on the coordinate grid here. I need to know, or I want to know, where is the graph? Holes and black dots, they're not what I'm going to focus on. So the graph itself is here. Okay, yes, there's a hole. But essentially, this is how high up or how tall at x equals 2, how tall this graph is. So the answer for A is 2. And it's 2 because of this number. Okay? I'll try to clarify this a little more in class. B, the limit as x approaches 2 of this function here. Okay, so once again, I want to look at x equals 2. Here's 2. And this is my x. I need to figure out where is the graph. This problem is a little different. It's special because if I look at the graph, it's broken up into two pieces. And part of the graph, which is this part right here, has a height of -1. I'll write it down right there. The other part of the graph, which is right here, has a height of +1. So here's my predicament. I've got two heights. Well, this is a two-sided limit. In order to figure out what the overall limit is, in order to answer this question, I need the two-sided limits. I need the limit from the left, which would be all of this blue stuff. And then I need to compare it to the limit from the right, which is the red part. And when I compare them, they have to be the same in order for that to be the limit. If they're not the same, then we use something called does not exist. It's a phrase. It's D-N-E. D stands for does, N not, and E exist. So I'd hope that you can tell, okay, this graph is broken. They're not at the same level, not at the same height. The limit from the left is -1. The limit from the right is +1. If you compare the numbers -1 and +1, they're not the same. This is how you would write it. So the limit of f of x as x approaches 2 from the left side, and this is how we denote the left. We use a negative. Negative symbol is going to tell me I'm coming from the left side. That limit is -1. Now, the limit of f of x as x approaches 2 from the right side, and the way to denote right side is positive, a little plus, that is positive 1. So if I look and I compare, obviously negative 1 and positive 1 are not the same. So since they're not the same, the limit of f of x as x approaches 2 is not going to exist. It does not exist. And those are two-sided limits. Example 2 also involves a graph. It says use the graph to evaluate the value of each given quantity. So here I'm asking you for a bunch of limits. I'm also not just asking you for limits. I'm actually also asking you for just values for the graph, or the equation if we had one, but there's no equation. So f of 1, that means if I look on the graph and I plug in 1, where am I? Where did I land? This is not a limit. This right here is not a limit. In order for it to be a limit, it must say LIM. There, I just want to know what the value is. So look at the graph. Here's 1. The only place that there is a solid anything is here. So that is my value for f of 1, and it is 2. Okay, if you look straight across to E, f of 4, I'm asking you the same thing. That's not a limit. Okay, I'm going to go in order. B, the limit as x approaches 1 from the left side, because this negative means from the left side. So let's see. There's 1 still. Now I want to look at the part of the graph that is on the left side. This part is the part on the left side. So from the left side, as it gets close to or right on 1, and remember this is 1 right here, I need to know how tall the graph is. How high is it? What's the height? So at 1, if I go up, here we go. This is how tall the graph is. Yes, it's a hole. It's not a solid line. But that is where my limit is located. That is not what f of 1 equals, but that is what the limit of x equals 1 from the left side is. And this looks like it's right in the middle of 3 and 4, so this would be 3.5. Okay, C. This time I'm finding the limit as x approaches 1 from the positive or the right side. So this is the right part of the graph. This is all the stuff that is to the right of 1. Same idea. I need to know how tall is this graph at x equals 1. So right here. At x equals 1, how tall is this graph? Well, it is located at y equals 1. So that is my answer for C. D. The limit as x approaches 1. There is no positive or negative right next to the 1. So therefore, this is the overall limit. And in order to answer the overall limit, I need the limits from B and C. I need the left and the right. I need to compare these numbers. Are they the same? Is 3.5 equal or equivalent to 1? God, I hope you say no. They're not the same. So when the two-sided limits are not equal, then unfortunately, the limit does not exist. And that's your answer. It does not exist. Now if you look at the graph at 1, it is split right at 1. So of course the limit can exist. It has two different values. All right, E. Before I start E, I'm just going to erase all of this stuff here, because I'm probably going to write some more. All right, E is f of 4. That means if I were to plug in 4, well, here's 4. What does my graph equal? And at 4, Look at this. There's a hole. Well, since E is not a limit, that hole makes a difference. So we say that it's undefined. There's no definition for what this graph or this equation, whatever it may be, equals when x is 4. F, limits. This time it's the limit as x approaches 4 from the left side. Right? The negative means the left side. Okay. This is the left side of the graph when it comes to 4. This is the left side. So as I'm traveling along the left side of the graph, as I get closer to 4, where do I end up? And I end up at a height of 2, or y equals 2. So that's my limit. From the right side, so from the right side of 4, right? 4. This is the right side of 4. As I'm traveling along the graph and I get closer to 4, I'm approaching 4, I need to know the height. Oh, the height is still 2. So that's the limit as x approaches 4 from the right, or the positive side. H, the limit as x approaches 4 of f of x. So this is the overall limit. It's not right or not left. It's the big shebang. So in order to answer the limit as x approaches 4, I need these two. I need to compare them. Are they the same? Does 2 equal 2? And yeah, 2 is 2. So since both the left and the right limits are the same, the overall limit is also 2. Example 3. Same idea. I'm using the graph to evaluate the values of each of these quantities here. Some of them are limits, some of them are not. The graph is a little more complicated. Just going to go through it. You can pause and rewind and listen to my explanations as many times as you want. A, that's f of negative 2. So I go to negative 2. Here's negative 2. I need to know what the value of the graph is at negative 2. And the only thing that has any value is this dot. So that is what I would get if I were to plug in negative 2 into this funky equation. And so my y value is 2. All right, B, the limit as x approaches negative 2. This time it is actually a limit. So I'm approaching negative 2 from the negative side. That's what this little negative means, right? It's from the left side. So I got to look at the graph and figure out, okay, what part of this is the left side. So here's 2. That means that all of this on the left side of negative 2 is the left side. Go figure. As I get closer to 2, the graph is doing this weird thing where it's just going down. And I'm supposed to figure out what the height of my graph is. But it's just going down. Okay, so if I think about this, all of these numbers are negative. Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. If it keeps going, I'm going to end up with negative 100, negative 1000. Eventually, I'm going to end up with really, really big numbers. And since it's not going to stop, I'm going to end up with negative infinity. So that's my limit. Negative infinity. Now I do the right side. So to the right of negative 2, this is the part of the graph that is to the right of negative 2. It's doing the same weird thing as the other side. It's also going down, just down, down, down. So it's negative infinity as well. Now D, the overall limit as x approaches negative 2. Okay, so from what I told you before, this is where we would go ahead and be like, all right, let's compare these. Are they the same? And they are the same, which, okay, so the overall limit is negative infinity. And that's half right. Because these are equal, the overall limit is negative infinity. But what is negative infinity? Do you know what number that is? I don't know what number that is. So because of that, an acceptable and correct answer is also does not exist. The limit doesn't actually exist. And if you think of the number the word infinity and the word limit, infinity means there is no limit. It has no limit. Okay. E. Back to values. This is not a limit. So at x equals 0, what does the graph actually equal? Let me erase all this stuff because you can pause and rewind, right? Right, so looking at the graph, this is the only place at x equals 0 that has any value. So f of 0 is 5. I wouldn't use this one because it's a hole. And this is not a limit. E is not a limit. Holes are okay for limits, but they're not okay for when I actually need a value. F of negative 4. So where's negative 4? Here's negative 4. This, again, is a hole, so that's not going to work. So the answer is 0. Now they want me to find the limit as x approaches negative 4 overall. This is left and right. So from the left, here's the left. What is the height? Oh, look at that, 2. Well, here's the right. What is the height as it gets closer to 4? Look at that, it's also 2. They're the same, so the limit is 2. H, the limit as x approaches 0 from the negative side. So again, I'm going to erase all this stuff here. And the limit as x approaches 0 from the negative. So here's 0. And the negative is the left side. So this is the part of the graph that's actually on the left side of 0. Huh, that looks like an 8. Great. Let's just leave it like this. Okay, so what is the height of the graph? Well, here it is at a height of 0. So that's my limit from the left. Now I gotta do the limit from the right. Okay, so again, here's 0, right? All of this is 0. This is to the right of 0. Actually, all of this. But what I want to know is, when it gets to 0, what is the height? Well, here's my height. That is how tall the graph is at x equals 0 from the right side. And that's 5. And then finally, J. The limit as x approaches 0. So this is the overall limit. This is when I have to actually compare this and this. Are they the same? Hopefully you can tell they're not. And therefore, does not exist. Let me write it in another color because, yeah, does not exist. Okie doke. Only 2 examples left. These shouldn't take long because I did all the really hard work. But the fact is that you're going to have to learn how to do this on your own. Like, get the values using your calculator. This is the numerical part. Example 4 is estimating a limit numerically. Remember, numerically is when you have to use a table. I have a equation, or an equation, but I have no graph, which is usually the idea with finding a limit numerically. So to start you off, ease you into it, I picked out the numbers already. I have the table set up. Your job would basically be plug in all of these numbers into the equation. And once you've plugged them in, you would get a y value, an answer, right? So I did all the hard work, and I'm going to share the numbers that I got. So for when I plugged in 3.9, I got 0.20408. That's a little long. In this class, You should get used to using 3 decimal places or 4 decimal places. 4 decimal places is safer. 3 decimal places is a requirement. So next, plug in 3.99, and I get 0.2004. Then I plugged in the next one, and this is what I got, 0.20004. And then so on. So I'm just going to fill these in. You get the idea, right? Hopefully. And usually these numbers do look a lot alike. That's just how they end up. Okay, so the idea is that I am looking for the limit as x approaches 4. And this, of course, would be my function f of x or g of x or h of x, whatever of x. So I'm looking for my answer. And if you look at the table, I didn't actually incorporate the number 4, but you could figure out where the 4 goes, right here. This is where the 4 would go. Now, this part would be the left-hand limit. And then this part would be the right-hand limit. And the idea is, just like before, they should be equal. They should appear to be coming together towards the same value. So, from the left side, as I start here and get closer to the number 4, I need to make some observations as to what's happening. All right, so I have 0.204, 0.200, 0.200 again, but okay, so here I had a 4, and here I have another 0. It's easier to look at like, okay, this is basically 2040, and then 2004, and then 2000. And what's happening to these numbers? They're getting smaller. They're getting smaller, but like what number are they getting closer to? So 2040, 2004, 2000. They would appear to be getting close to 2000, or 0.2000. From the right, start here. I'm going to move in and get closer to 4. I have to make the same observation. As I come in from the right, what is happening to these numbers? So let's see, I have 1960, 1996, and 1999. These numbers are getting bigger. And as they're getting bigger, what number do they appear to be getting closer to? Well, 1999, that's basically a step away from 0.2000. I think it would be very safe to say that the limit, the overall limit of f of x as x approaches 4 is 0.20. And that's how you do a limit numerically. The next one is the same idea. You could skip it if you think you got it, or you can listen for a few more minutes. Example 5 is the same idea. I have an equation. I have a table set up. I already put in the values into the table. Those are the values I got when I plugged in each number. Here my limit is as x approaches 0. So let's see, 0 would go here. So again, the left and the right. This being the left, and this being the right. And then I just need to pay attention to where are these numbers headed. So starting from the left, heading towards 0, I see I have 2049, 2042, 2041. They're getting smaller. And they seem to be getting closer to 20, let's say 40. From the right, start here and head here. Let's see, 2032, 2040, 2041. They seem to be getting bigger, slightly of course, and heading towards 2040 as well. Look at that. So since they're equal, that is my limit. 0.204. That's it. At this point, you need to look onto your assignment schedule and to see what problems you have to do from the book. Please feel free to pause, rewind, replay. Okay, see you in class.